Hello, everyone, and welcome to today's Real Data Science Meetup. It's lovely to be with you all on this sunny afternoon to discuss reinforcement learning and how it could be used to build a swarm of drones, apparently. I'm excited to hear that. Joining me today, we have one of our data scientists, Alex Kell, who's going to lead us through the bulk of the discussion and dive into what is a really interesting application of reinforcement learning and data science. We also have another of our data scientists, Christian Motschenbacher, who will be leading a demo later on, but is not with us in the room today, unfortunately. Before we get to that, though, as usual, we're going to lead off with a brief chat. It's my favourite part of the session. We get to better know our team. So I'll be asking Alex some questions about his journey through his career in data science. And lastly, in case this is the first time joining for any of you, I'll give a quick intro on what these sessions actually are. So the Real Data Science live streams. This is a series of global live streams and in-person events running every 6 weeks out of London, Utrecht, Denver, and Copenhagen PA offices. Data scientists from across our team go deep. They present a blend of theory, code walkthroughs, historical context for technical areas of interest in data science, AI, and machine learning space. The hope is that these sessions are fun and you enjoy them and you learn something as well. But also that they start to open up a sort of broader community around sort of data science. It's the way that real ground has always been made in the field, is through that discussion and engagement beyond the scope of just who you're working with in the day-to-day. So if you want to follow the series, see where and when upcoming sessions are going to be, or provide any feedback or areas you'd love us to dig into in the future, follow us on our Meetup network or subscribe to the YouTube channel at Real Data Science, and you'll see what's coming up down the pipeline. So with the intro out the way, I'm excited to open up the session with a bit of a chat. So Alex, thank you for joining us.
No problem.
Firstly, I guess this is the one we always open up with. It's sort of the easy one, but I think it's often quite telling. What's the sort of path of your career? What's led you to be here today, a sort of data scientist, talking about reinforcement learning, talking about drones, and possibly some more at PA Consulting?
Yeah, so I have always been quite technical in nature. So I've always loved computers since for a young age. I've always been trying to learn as much as I can about computers, getting my dad to teach me and things like that. So for me personally, it's not the same for everyone. I wanted to stay within that field. I knew from quite an early age. So if I skip forward to my university degree, I knew that computers or engineering was something I wanted to go into. So I decided to do electrical and electronic engineering because that gave me a good fundamental basis in how computers work. And so I did that, and I found that what I most enjoyed wasn't the circuits and the analysis and those things. It was more the actual coding side of things.
From hardware to software.
Exactly, the full stack. So what I did, I then decided I wanted to learn about the world in a different way. So if I were to do web development, that wasn't my sort of thing, so I'm not design orientated, but I wanted to use computers to learn about the world and to come up with interesting answers to uncommon solutions. And so after a brief stint in industry where I was doing more business things, I did a PhD in computer science.
Oh, wow.
And I did a whole PhD in electricity markets. So it was a lot about how can we predict how electricity markets will develop, how basically the story was, how can you get to net zero by 2050, and what policies should governments put in to reach that target. So we simulated lots of policies, we simulated lots of economic investment scenarios, and then we ended up with some results and to sort of present. So that was my PhD.
Yeah.
And it was a lot of interesting ideas came forward, including reinforcement learning. And then I did a brief stint at a postdoc, research associate, and then still in energy markets. But I thought I wanted to see how could my work impact the here and now today, rather than 2050, which is a long goal. How can I help clients today and give them value? So that was how my journey ended up bringing me to PA.
That's really fascinating. We've never discussed this before together, and I never knew that your research was in an area actually in the sort of reams of research and how broad it can be, that's actually very sort of feels very pertinent to today. And actually, from that position, still there's that feeling of, but I want to make an impact right in front of me. That's really, really interesting. And actually, that story of starting out being interested in hardware, studying sort of how you actually build electrical circuits and electrical engineering, through to more of the software coding, sort of logical side of things in that sense. There feels like there's a wide breadth of skills you utilize and work through across those different, I guess, fields. Today, where you sit doing primarily data science, machine learning work, what skills do you find actually are the ones that you are utilizing most or feel most important to you? Because I think sometimes the answer can be surprising when I talk to people about this.
I think the number one thing that I've learned is the learning process. So it's sort of like, I joined PA and I had not much experience in the water industry, but I've been able to use the analytical skills that I've got, that I've previously used, and say, how can I do this to a new industry, and how can I help a new client for something that I've never heard about before? So by working with experts at PA in the water industry, for example, or healthcare, I'm able to deliver for them and add value through my analytical capabilities without being the foremost world expert in water, but through tight teamwork, we can often deliver good results.
So it's sort of like a team synergy and a bringing those disparate or at least distinct skill sets together to improve what either one could be delivering separately. That makes a lot of sense. I guess following down that rabbit hole, are there any particular pieces of work or things you've accomplished during your time at PA? I guess maybe in particular of reinforcement learning, if anything jumps to mind, given it's the topic of the day, that have really stood out to you as memorable or cool.
So I would say the value that we add in the water industry, which I've been working a lot with, is it's not just about the foremost state-of-the-art models, but it's using the foremost state-of-the-art application knowledge into modelling, which really adds value to the client. So it's not just about, I've sort of seen, it's not just about the coolest technology, it's actually about what the most valuable technology is. And that can add real benefits to clients, bottom line impacts, that has a lot of impact on a financial sense, but also a process sense, saying how can they do things better, what data should they collect, how should they collect it, and how can they make better sense of it, because it's quite often that sometimes these skills are lacking within the wider community with data science skills. So by bringing these skills to certain applications which haven't had that amount of research, they're big impacts that I've seen.
Yeah, it makes a lot of sense, and I find so often it's easy to oversimplify or almost reduce a bit too much what's going on and think, yes, there's a solution we want to apply, or there's a technology to apply, when often the most interesting part of some piece of work and where you learn the most is thinking, well, no, what is the thing that is best for this? That's a whole avenue to explore on its own, and sometimes gets overlooked. That's really cool. Well, I don't want to grill you for too long. I know you've got some really exciting slides to talk through about reinforcement learning, and then later on we have Christian's walkthrough as well. So I'll hand over to you now to start talking us through the bulk of the presentation. But thanks, Alex. It's been
thanks,
fun.
Max. Thank you. So hi, I'm going to talk to you a bit about reinforcement learning, which is a state-of-the-art technique which allows users to control their environment or make decisions within their environment to get optimal rewards. So it's different to other machine learning techniques. We haven't necessarily got, we can have the data, but we haven't always got the data. We just have a model of the world and we interact with that to get the best outcome for us. So that could be anything, and it's being used to great effect with ChatGPT. So we train that the users trains the data to say what the users wanted, and the model automatically worked out how to best present the data to users. And that's how ChatGPT works with reinforcement learning.
Very topical.
Yeah. So if I jump to the next slide, effectively these are some of the things that have been done with reinforcement learning at the earlier stages. So these figures that you can see, there's 4 games that you can see. and they are all controlled by an AI. They had no idea how it was done before. We didn't tell them that you had to, for instance, get the green dot if you're a snake, but just through trial and error and multiple simulations and many iterations, very, very quickly, it learned to play snake better than a human. So we didn't do much. We just set it up, click play, and then it worked. A bit more complicated than that because you have to model the environment or the game, but effectively you just click play and it learns how to do it.
That's fascinating. It's a perfect use case, right, for reinforcement learning, and yet I don't like the idea that the computer's already better than me at Flappy Bird.
Yeah, yeah, and that was done, I think, by DeepMind, these Atari games. So if we go to the next slide, we can see what it's like actually in the real world. So if we can see here, we see just a cart pole environment. So it's a weight on top of a stick with a sort of a moving pivot at the bottom. And at the start, with no training, we see before this is when somebody's trying to do it themselves. They're moving from left to right. So there's a human trying to do it. Then we see what happens if it's a neural network to this, and it's working
so
really well. It's actually staying up, making decisions very, very quickly, very fast speeds. And then we have another one where we use some genetic programming to optimize it even further. And now we can even see that it's shifting from a bottom position and swinging up to the top position. And finally, we can say what happens if somebody comes along and pushes that thing and tries to mess up the system, it can still do it. So if a person were to do that, they wouldn't be able to do it. It's all a computer. So that's the power of reinforcement learning. So I just wanted to give you a quick overview of some of the applications that you can use reinforcement learning for. So healthcare, education, transportation, and energy. But there's not all of them. If you can think of an application yourself where you need to do something to do an action to gain a reward, then reinforced learning would be used really well for that. And so it's a really great tool that you can use to maximise the reward in this particular game or environment or something you want to do.
And I guess that must be kind of key to it, is that there needs to be a way of capturing or encoding or modelling that environment that the repeated action is done within.
Exactly. So that can be the difficult part sometimes. Yeah. You have to do a whole simulation of this environment, and you have to you have the algorithm and the environment, and you put the two together, and then sometimes you get great results, and sometimes you have to try again.
Always the way.
Yeah. So just to give you like an introduction to reinforcement learning now, we have supervised learning, unsupervised learning, and a separate branch of that is reinforcement learning. So where we have labeled data in the supervised learning case, we have no labels in the unsupervised learning case. In the reinforcement learning, as Max mentioned before, we have the environment that you have to play within. Yeah. And the goal is to learn a series of actions which will maximize the cumulative reward going forward. So I'll get a bit more into this later, but how do we, for instance, make as much money as possible from a bid or things like that? Or how can we reduce waiting times in a healthcare setting? So now we get a bit further into sort of the details of a reinforced learning scenario, where we would say the algorithm is this man in a suit in this example, and the environment which Max spoke about is what we have to code up and say this is the game that you're playing. So in Snake, the walls are around here, and the food is a green dot in the middle, and then we do the Snake, and you have 4 actions: up, down, left, and right, and that's the action space. So we also see the output. So in the Snake example, if you go into the wall, then the output is game over. Yeah. So we teach the algorithm game over, and then we have a reward, and the reward could be -100, -200, or something along those lines. If you go into the wall, you might get a reward of 1 if you eat the food, and you might get a reward and that will cumulatively add up over all time steps. You might have 100 points by eating 100 food in a row.
That makes sense.
And the state is a separation of the output from the reward and the state. So the location of the snake as well comes into that. So that's the state and reward.
Really interesting. Well, really interesting to hear, and I might be about to land a sort of horrible question in your lap, so no pressure. You're talking there about, I guess, weightings for the reward function, effectively, or what it is, and some of those outcomes. You threw out some numbers sort of off the top of your head to sort of say, wall bad, pellet good. How much tuning of those sorts of numbers comes into it? Would it make a massive difference if you're dealing with 1 and minus 100 or 2 and minus 50?
So it does make a difference. I mean, it's all relative.
Yes, of course.
So if you made 100 for eating the food and minus 1,000, and it's all relative, it wouldn't make too much of a difference. No. But you would then scale it back to the neural network to do that. But there's definitely an important part that's called reward crafting. So you would basically say, do we want to give it a reward just once when it eats the food, or do we want to give it a reward as it gets closer to the food?
I can imagine in more complex environments and scenarios, then there's a more thought that would need to be put into that reward crafting than snake, which is pretty straightforward. Yeah,
definitely. But there's been great results in doing minimal reward crafting.
Really?
So there's a wide. Every application is different. You have to approach every problem differently. Try with what you know, and then iterate, and you should get good results.
That's why it always comes back to the trial and error of it all.
Exactly.
Nice.
So now we're going to go into a bit of a deep dive into the algorithms. And we're going to focus on one specific algorithm called Q-learning, but we're going to get to that next. So just at a high level, the reinforcement learning, within reinforcement learning, there's a huge amount of algorithms, and it can be a bit confusing when you first come to it, but the main sort of categorizations are value-based, policy-based, act critic agent, model-based, and model-free. So in a value-based algorithm, you are just trying to maximize a value function. So we're going to get more into value functions later, but effectively we want to know what reward we're going to get, and that's part of a big matrix that we see. But we'll get into that later. Policy based, we have an action and value function. So from this action, move up, what value, what reward do we expect to get from that? So it's a prediction of what we think we're going to get from a particular action. Then there's actor critic agent, which is a mixture of the two, and it stores both the policy and how much reward it is getting from each state. So it's a mixture of the two basically. Then there's model based, which we as a user we create a virtual model for each environment, and we sort of let the algorithm know about that. And then model free, where the model just trial and error, and it gets lots of information back, and it tries to work out what it should do. So if it keeps hitting into the wall 10 times, it will get minus 100 reward. But if it eats the green food once, then it's going to get a reward of 10. And then it will say, I should not go into the wall. After 10 or 20 or 100 times, it will eventually learn that.
So just seeking that reward.
Exactly. Just trying to do things which are going to maximize the reward.
Absolutely.
So Q-learning, just the high-level technical details, is a value-based, model-free reinforcement learning algorithm, which is what we saw. So that's how it fits into the previous category. As I said, the goal is to learn which action to take. It does not require a model, so we just give it data. We just let it sample from the model. And it can handle stochastic transitions and rewards. So that means when the person in the previous video was pushing the weight, it can deal with that uncertainty. It can learn to say, I've not been pushed with this force before, but I've been pushed with similar force before, and it can learn from that and interpolate and do all those clever things. But for a finite system, for any finite Markov decision process, which effectively means with any game that has a certain amount of actions and rewards and states, and that's finite, so it's not infinite, we can get the best game. We can play the best game and we can win that.
Yeah.
Mathematically, theoretically. Now, the real world, if it's too big, it might not do it, but mathematically, with enough time, enough iterations, it should do it. And the Q is just a name that returns the reward used to provide the reinforcement and can be said to stand for the quality of an action taken in a given state. So it's just Q just stands for quality.
That's actually useful to know. I never knew that.
So now this is we're going to go into a bit of a different environment. So let's say we are in room E and we want to get to room F. So F being the green one. When we start, the reinforcement learning algorithm has no idea, but if we say that from B to F we give it a reward of 100, and if you stay at F you get a reward of 100, and everything else you get no reward. So it's a bit difficult for the game to learn the first time because it might move from E to A, and then it gets 0 and it says I don't know what to do next. So then it has to try E to D, and it might not know what to do next until it finally gets to F, and then it will get 100. So there's a lot of moves it has to make to get that 100, but we can then use mathematics to roll back and to update our expectations. So I'm going to get a bit more into that now. So if we start from that game that we're playing, we start at E, and then in the top matrix we have E on the vertical axis, and then we have, if we move to A, so A is the first one on the horizontal axis, we get 0 reward. But we can see if we go from B to F we get 100. And if we go from F to F we get 100. So it's still quite a sparse matrix. We don't know what to do, but we can use it. So that's the first part. That's the current state and action. That's the first RSA in the equation on the right hand side. But we also want to say what could happen in the future. So in the future, if we go from E to D, we're close to getting from B to F. So, but we are not always the most interested in the future reward, because we might want to prioritize the current reward. So we won't want to eat as much food today and not have much food tomorrow, is all it's saying. So we have a discount rate, which is a number between 0 and 1, which says how much importance is tomorrow compared to today. So that's just the gamma there, the discount rate. And then we then can put into the function the expected transition, the next state action we're going to do into the future. So it's a bit complicated in a minute. I'm going to now jump into what that actually looks like. So that's the Q-learning algorithm. That's the main algorithm of Q-learning. So if we go from D to B, if you see in the matrix on the right-hand side, we have now updated our model to say we think we can get, that's worth 80 points, and a reward of 80, because we get 0 when we move from D to B, but after we've got that 0 reward, we will then get 100 when we move from B to F. But that 100, one time step later, is worth less than it would have been today, because we want to maximize our reward today, because and in this example we do want to maximize today a bit more than before, because then we might get there quicker, basically.
Absolutely. That seems like one of the key parts of this discount factor, and because if getting there 1,000 steps in the future is going to give you the same reward as getting there one step, it's sort of, you're running down a route where in certain scenarios I'd imagine you end up with inefficient, at least within the scope of the game or the scenario itself, solutions.
Exactly, that's exactly it. So we can update it to say we're happy from D to B, we're happy to get 0 today and we're going to get 100 tomorrow, but that is worth 0.8, that's 80%, so that's 0.8 times 100 is 80, so 0 plus 80 is equal to that, and that gives us the action state transition from D to B, and you can see that there. So that's just one movement of one iteration working back, but if we keep trialing and error, we just keep doing that over and over again, we end up with the state, the action value, the transition matrix from D to B is 80, but then from D to C is 51, because we're moving away from the goal. And so once we've filled out this matrix by iterating every single time that every single possible transition, we can just maximize this function. We can just say, I'm just going to choose, when I'm in D, I'm going to choose B because 80 is higher than 51 and it's higher than the other 51 moving to E. So we can just maximize the reward and just do the maximal possible thing possible. And that will give us the right answer most of the time. Well, all of the time in this example. But that's without saying that there's stochasticity. So what happens if the room changes around? What happens if F moves to the bottom and all that sort of thing? So it's actually quite a simple fix. We just take a random action, say a certain percentage of the time. So we think we know we should move to F every time, but sometimes if the reward changes, we have to say 20% of the time, let's not do F, let's do a random action and update the matrix in a different way. And that allows us to actually model new environments or changing environments going forward.
It's incredibly cool. It's the bit that starts to blow my mind a bit, because when you think about the set environment and you think about, well, there's only realistically a finite number of things, even if it starts to get more complex, and if you, again, we've made these assumptions about being able to solve it with infinite time, etc., or reach the reward, etc. But that it can be so effective to just introduce that randomness.
Exactly.
Is just very cool.
Yeah. And that's just known the exploration-exploitation trade-off. So the best idea is if you go to the same curry, to the same restaurant every time, you get the same curry, you might think you've got maximum reward, but actually, if you try a new one randomly 20% of the time, you might get a curry you prefer more. It's as simple as that.
Yeah.
And so we can add that into the action equation by with a learned value. So we have an action. And we just iterate it, just randomize it at 20% of the time, and that's effectively what that equation does. So now we're going to get into the drone challenge, which was spoken about. So effectively, what we've done at PA is we have a number of drones that you can see at the bottom of the image, and the blue ones are our drones. And we want to have communication between each of the little stick men across this whole country. And we want that to be kept there all the time. But these red drones come in and they block our blue drones, and they stop them from communicating. So if we can see in this example, the two on the right are completely disconnected from all the other guys on the left-hand side. So what we could do is we could have a bunch of people all controlling their own drone.
Yeah.
But that's time consuming and it's not optimal, because if we can get a computer to do it better, it'll be cheaper and it will be more effective.
And so effectively this, within the realms of what you've described of being a reinforcement learning or a problem of reinforcement learning opportunity, this does fall in it, because it looks like we've got a game that's boundaries and constraints can be modelled.
Exactly.
And that, as you say, a computer could probably do it better.
Probably can, yeah. So we just want to put an algorithm on there, click play, and then run the model and get good results. So that's what the game looks like. And this is a multi-agent problem, multi-agent reinforced learning problem, which basically means that we have multiple different agents all trying to interact in the same world. So it adds complexity quite a lot. So it's quite simple in the rewarding of this game. The reward is negative at all times. We just want to be as close to zero as possible. The more negative, the poorer the agent. So -100 is worse than -50.
Yeah.
Now, if the red team controls all the blue drones, then it's then we get a penalty, and the rewards for each of the agent events are shown in the table. So if data transfer is blocked, if we can't communicate from one drone to the other drone, then we get a -1. We get a -1 reward. If data is intercepted by a red agent, so if the red agent sort of knows what we're trying to communicate, then that's another -1. if there's no bandwidth available, that's another -1. And if no data path can be established, that's a -1. So there's lots of -1s. But if all blue agents are removed from the board, then we get a much worse reward, which is the number of time steps left multiplied by the number of drones which are taken away. So if we lose all of our agents in the first minute, that's worse than losing all our agents in the last minute.
Absolutely. And presumably it means there's an end to the game. You're not having to last forever.
Exactly.
Interesting.
And that's very important, because the more experience, the more times you can play, you can show the reinforced learning algorithm the game, the better it is. You want to try as much as possible to give it as much experience as quickly as possible to learn as much as possible.
Fascinating.
So what do we want from this agent? Well, we want it to be generalizable, so it should be designed to perform well in diverse situations. So basically, if a red agent pops out from the top every time, it could learn to defend the top. If it comes from the bottom one time, we want it to be good at that as well. Has to maximize reward, which is what I've been telling you about from the start, and it's got to be robust. So it's similar to generalization, but it should be able to adapt to changes in the environment at all times, because if we can only solve one problem every single time and nothing new happens, then we're going to get stuck. And then we want it to do some exploration versus exploitation. So we need to improve the policy over time and not just get into a local minima. So that's sort of the environment. And now let's see the drones moving around.
This is what I wanted, absolutely.
So as you can see, it's all blue drones in this country, and we are able to maintain connectivity between the drones on this game. And they follow a swarm algorithm where they start from a random position and they swarm around to have local clusters which can have communication between the drones, where the black circle indicates the drone communication area. And then we can see at some times a red drone is going to pop up, and this is a real life simulation. So a red drone might pop up in a minute, there you go, and it's taking away some of the drones, but we still have communication from at the top. So this is sort of how the game looks like. So thank you. I think that is all I wanted to say, and I think we're going to hear from Christian now.
Absolutely. We'll pass over to Christian in just a second. Before we clip over to his walkthrough, I just wanted to reiterate, thank you everyone for joining us today. Do check out our Meetup network, Real Data Science, or our YouTube channel to see the upcoming events in the future. Again, we have live streams roughly every 6 weeks with a whole breadth of topics covering data science across our team. So big thank you, Alex. I really loved that presentation. I really want to take the game home and play it myself if there was a way. It feels perfect for a LAN party. And thank you again, everyone. We'll see you again soon. Bye.
Thank you.
Learning library RLLib, including a demonstration. To show you the difference between a random action performing not skilled reinforcement learning algorithm and a trained algorithm, I will start with a demonstration, explain the steps including algorithm training. As a high-level overview, start the training, which takes about 8 minutes. Once the algorithm is in training status, I continue with the presentation. Once I finish the presentation, I change back to the demonstration to explain the code in more detail and show you the result of the trained algorithm. Now let's change to the demonstration. Okay, unfortunately, I cannot show the drone example, which Alexander mentioned, because it requires too much compute for the algorithm training, and therefore it cannot run on my local computer laptop. Instead, I set up the cardboard example, which my colleague Alexander introduced in the beginning of the presentation, and which he also showed. In the first cell, basically, I'm importing the library. I'm executing this cell. As you can see here, it is running. In the next cell, I'm using random action to control the environment. As you can see, the control of the cardboard is not good. So, sorry, I need to start. Okay. As you can see, the control of the cardboard is not good, falls over quickly, and a new episode starts. The low performance of the random action can also be recognized on the low episode report here. In this cell, I'm closing the rendering of the environment. Here, I'm shutting down eventual running array clusters. In this one, I'm configuring the environment and the training algorithm. And now in this one, I'm performing additional configuration of the checkpoints when the algorithm should stop and start the training. Okay. The training now is in, or the training now is in, training has now started. Okay, then let's go back to the presentation. RLLib can be used to solve real-world reinforcement learning problems. Ray is an open source library for distributed computing, including data processing, machine learning, deep learning, algorithm training, including hyperparameter tuning, serving training models, and enabling distributed computing for data processing of Mortin, Hugging Face, Apache Airflow, and other tools. It's easy to use solution for training agents in multi-agent setup from offline datasets or using external connected simulators. RLLib is used in climate control, industrial control, manufacturing, logistics, finance, gaming, automobile, robotics, boat design, and many others. Here you can see Ray can run on a local machine, on a laptop, on a desktop. It can also run in the cloud, AWS, Azure, GCP, and the good thing is in the cloud, basically, Ray scales quite good over multiple nodes and clusters. In my particular example, I'm using RLLib library for training the algorithm. In addition, I'm also used the Dune library for hyperparameter tuning. However, this library's array platform can be used for data processing, as mentioned here, Mortin. You can train your algorithm with Hugging Face, and you can, once you have it trained, you can serve the algorithm with Ray Serve. And of course, you can also enable the distributed computing of the library here, for example, Apache Airflow. Now I would like to explain a little bit more about the features and the customization of the libraries. RLLib API stack is built on top of Ray, offers off-the-shelf, highly distributed algorithm, policies, loss function, and default models, including the option to auto-wrap a neural network with a LSTM or an attention net. RLLib provides simple API to customize all aspects of the training and experimental workflows to get the best results. For instance, the built-in environment and algorithm can be used as they are, modified or replaced by custom environments and algorithm. Contains built-in server-client setup, allows a connection of hundreds of external simulators, clients. RLLib offers a simple solution for training agents in multi-agent setup and from offline datasets. RLLib supports also TensorFlow as well Torch, which can run on 100s of CPUs and GPUs and even more. Here you can see this is Ray in the lowest level. Then on top of it, you have Ray RLLib libraries, and as well all the other functionality. Here you have the built-in algorithms, additional add-ons. In addition, you can create your custom model, can develop your custom model with TensorFlow as well, PyTorch. And of course, you also can use your custom environment. In this slide, I would like to tell you a little bit more about the built-in algorithm. This is only extract of those some of the algorithm. The algorithm can be clustered in offline learning, model-free, model-based algorithm, as well multi-agent. In addition, it also has some reinforcement learning for recommendation system. The algorithm which are listed here and as well here, they can be differentiated and they have different functionality. One of the differentiation is you can use some algorithm for discrete actions. For example, when you control a car, left, right, forward, backward, for example, a simulator, or you can use some algorithm for continuous action. What I have done is what I will do for controlling a card bowl. Some of the algorithm can be used with multi-agent and one only for single agent. And of course, in addition, you have some add-ons here for the model support. We have, for example, add-ons like LSTM, AttentionNet, which help to achieve better results. Okay, then let's go back to the demonstration. And let's see what is the status of the training. Okay, the training is still in progress. It might need a couple of more minutes, but regardless, I will start from the beginning and will explain the code a little bit more in detail. And then usually my experience is it should be finished in about overall 8 minutes, or yeah, maybe 10 minutes. Okay. In this first slide, and in this first cell, I'm importing the libraries. The main library is basically Race, a distributed platform. On top of it, I'm using, for example, for hyperparameter tuning, the tune library, and as well, of course, the RLLib libraries. And the algorithm here, I'm using in particular the BBO config. And here you already can see the example, which is built in the documentation. In the next, in this cell, I'm in this cell, basically I'm controlling the environment with random action, which means here I'm setting up the environment itself. Here I'm having 2 loops. One loop is for the epochs, and another one is basically for the episodes, and then it iterates over, and then basically it gives you the result. Here you can see the low episode reward results, which show that the random action do not perform well on this environment. As already mentioned, in the next cell, I'm closing the renderings environment. Here, I'm shutting down eventual running ray clusters, because if you start multiple clusters, it can cause issues. In this code cell, basically, I'm configuring the environment as well as the algorithm itself. As you can see here, I'm using the card bowl example from the Gymnasium library. I'm setting up the training. Here, in particular, I'm setting up the grid search for the learning rate itself, for the neural network in this algorithm. Then as well, I'm specifying the framework, I'm specifying the rollout workers, resources per experiment, and as well as the evaluation. In addition, I'm also specifying our paths for the checkpoints. In this next cell, I'm basically performing the training. Here, I'm using the tune tuner. In this tune tuner, you can feed multiple parameter inside to specify what algorithm you want to use. Here, I'm basically assigning the parameter space. Here in the run config, I'm specifying the condition, how long it should run, and what are the stop conditions. As you can see here, this is the name. This is here the name, the checkpoint path, and then here basically I'm specifying to run this for 10 iteration, 10 epochs. However, you also can specify, for example, the episode reward mean as a stop. However, in this particular one, I wanted to run this for a specific amount of iterations, not that it takes too long. And of course, you can specify the checkpoint. Here you can say how many checkpoints you want to keep, what checkpoints you want to keep. You can specify here, I'm using, for example, the reward mean, the maximum, and the frequency of the checkpoint. And as well, I want to keep the last checkpoint. Here you have some overview about the training status, when has it been started, the memory, what is being used, the resources of the CPUs. Here you can see that I'm basically running 3 experiments with different learning rates, what I basically specified here in the configuration. This is a grid search here, learning rate 0.01, and then here, and as well as the third one. This runs basically now in parallel on my laptop. Here you already see some of the results, how many steps has performed, and as well, maybe I can quickly come here over. You see, for example, the iterations, the rewards. Here you can basically see the intermediate result. In the next one, in this one, I'm basically retrieving the algorithm with the best episode reward mean, because I want to store them, save it, and want to use it for later inference to control the environment. This is what I'm doing here. I'm retrieving it. I'm storing this on the hard disk itself. Here I'm shutting down the array cluster. And then here in the last one, in the last cell here, I'm resetting up the configuration of the environment, setting up the frameworks itself. And then here, what is important here is where it is, yes, okay. Here, basically, I'm specifying the file for the checkpoints. And then I'm building the algorithm itself. And then here, I'm basically loading the checkpoints itself from the file. And then what I'm doing here is I'm controlling the environment with a trained algorithm. And then, of course, in the end, I'm closing the rendering. So let's see. Okay, so the training has been finished. It has taken 8 minutes and 40 seconds. It took a little bit longer. I think the recording also needs some resources, and then this was a reason for this. Okay, now this has been done. Now let's continue with this one, basically retrieving the best training results, shutting down the array cluster. As you can see, I'm running this locally and it runs quite quickly. So now let's load the trained algorithm and let's run the trained algorithm on the environment. As you will see, the visual results and will be much better, as well as actual episode reward mean. Okay, here you can see the trained algorithm control is much smoother. It do not fall over, and the episode do not restart again. And then here you can also see this here, that the episode reward is basically 500, which is the maximum for this. Now I'm closing the rendering. This was this example. In addition, I want to show you a nice add-on. This is basically some now I want to show you the training results in the TensorBoard here. I just will refresh the results because the training has been finished. Okay, so now here we'll filter for rewards. And then here you can see basically here is a reward mean. And then what you can see here is a training started and over 40,000 iteration, the reward mean increased significantly and continuously itself. Of course, you have many other metrics as well, which you can use to analyze your algorithm, debug your algorithm, and can improve it. Here, for example, you have the reward max. It means in some of those episodes, you have basically, you reached this earlier. Let me scale this a little bit. Let's take the smoothing off. So what you can see here is there was already some occasion that the blue and the pink experiment reached the maximum of 500 already after 5,000 iteration. Of course, this was one time. Usually you train this for a longer period of time, that this result is stable and is repeatable, and is not only, you have not only reached this one, that the algorithm will achieve a better results. So another nice thing of this built-in TensorBoard is here's a hyperparameter. As mentioned, I run 3 different experiments. You can visualize those with a parallel coordinates view. And then what you can do now, you can come here and then you say basically is episode reward mean here. You can click on it. And then in this episode reward mean, you see the maximum what we have achieved here is here 319. Of course, earlier on I had this inference and it already shows 500. But it depends, if I run this longer, then it has continuously 500. But the interesting thing is now here you have this experiment with a most episode reward mean of those 3 experiments. And then if you go through, you will see the specific parameter for this. And here in particular, I was interested what is the best learning rate. And in this one, the best learning rate is basically 0.001. Okay, this was a distributed data processing platform, Ray, including the reinforcement learning library RLLib in theory and praxis. I hope you enjoyed. Thanks for joining me in this session, and I wish you a nice day. Thank you very much. Bye-bye.